Good morning everyone. Myself Muskan from B.Sc Chemistry Honors Second Year. Today I am going to make an audio recording lecture for visual impaired students on chapter Chemistry of Actinides of Inorganic Chemistry. Actinides constitute a series of elements following actinium atomic number 89 in the 7th period of the periodic table. Actinides belong to F block as these are formed by the gradual filling of 5F subshell. We have discussed the chemistry of lanthanides in the previous chapter. Lanthanides, which follow lanthanum atomic number 57, involve the gradual filling of 4F subshell. In this chapter we will discuss the chemistry of another series of 14 elements which follow actinium atomic number 89. This series of 14 elements is called the actinides. Actinides along with lanthanides constitute complete F block elements. The ending "ide" in actinides is not appropriate because it more correctly means negative ion, such as oxide or chloride. Actinides were also named actinones by a group of scientists. However, the ending "on" is used preferably for non-metals such as boron, silicon, etc. Whereas all the actinides are distinctly metallic. IUPAC has now recommended these elements to be called actinoids with the ending "oid" rather than being called actinides or actinones. However, it is unfortunate that people still call these elements by their earlier name as actinides. Before World War II, the only natural occurring actinides namely thorium, Th, protactinium, Pa, and uranium, U, were known. Uranium is the heaviest naturally occurring element. It was after World War II that the remaining elements were artificially discovered through nuclear reactions. These elements are named man-made or synthetic elements. Another named coined for these elements is transuranic elements. Transuranic elements are elements that have atomic number greater than 92. Let us now discuss the interesting aspects of the chemistry of actinides. Position of actinides in the periodic table. An inspection of the periodic table reveals the electronic configuration of noble gas radon as Xc54 6 S2 4F14 5D10 6p6. After radon, the 7s and 7p orbitals gain stability relative to 5f orbitals because s and p orbital are more penetrating than the d and f orbital. As a result, the next two electrons are being filled in the 7s orbital, which mark the appearance of new elements: Fernentium atomic number 87 and radium atomic number 88 belonging to S block of element. After the addition of the 2 electron in the radon core, the 5f and 60 electron penetrate the 7s orbital. The least penetrating f orbital are stabilized on account of the increase in effective nuclear charge outside the next noble gas core with increasing atomic number. As a result, the next 14 electron from thorium to lawrencium atomic number 103 enter the 5f shell. It is important to note that around actinium, both the 5f and 6d subshell possesses almost similarly energies. Because of similar energies of 5f and 6d subshell, the incoming electron may enter either of the two subshells, which result in the uncertainties of the electronic configuration. As a result, it is doubtful whether the electron enters the 5f orbital or not. For example, the configuration of thorium atomic number 90 may be written as either 5f062 7s2 or either 5f161 7s2. However, once filling start in f orbital, the 5f subshell become more and more stable. As a result, from uranium onward, the 5f shell becomes most stable. Thus, all the incoming electrons starts filling progressively in f orbital. The general electronic configuration of actinides can be assigned: radon Rn 5f0 to 14 6d 0 to 1 7s2. General characteristic of actinide. Some of the general characteristic of actinide are detailed below. Electronic configuration. Number 1. As already discussed in section 5.1, the actinides involve the gradual filling of 5f subshell. The electronic configuration of the title actinium atomic number 89 is Rn61 7s2. Thus, from thorium onward, the 5f subshells start progressively filled. The general electronic configuration of the atom of actinide in the ground state may be written as Rn 5f1214 6d0217s2. The detailed electronic configuration of element presents. Number 2, physical properties. Some of the physical properties of the actinides are present. Melting and boiling point. The melting and boiling point of actinides are moderately high but are lower than those of transition element, and inspection of the table reveals that there is no regular trend in the melting and boiling point of the known actinide. Actinium melting point 817, boiling point 2470, density 10.0, radius 1.12. Thorium melting point 1750, boiling point 4850, density 11.72, radius 1.80, etc. Density. An inspection of table reveals that the element near uranium have very high density. Americium resemble the corresponding lanthanide, europium in being less dense than in its neighbors. Ionic radii and actinide contraction. The size of the actinide ion decreases regularly along the actinide series. This is because with increasing atomic number, the extra charge of the nucleus is poorly screened by the F electron. This steady decrease in ionic radii with the increase in atomic number is called actinide contraction. A comparison of M3 positive ionic radii of actinides with those of the lanthanides reveal that there is actinide and lanthanide ion are very small, similar in size. As a result, their chemical properties are also similar. The decrease in the ionic radii of M3 positive and M4 positive ions in case of actinide is shown. It is interesting to note that there is a decrease in the atomic radii from thorium to uranium, which may be due to the decrease in the most stable oxidation state from +4 to +6. In other words, the metallic bonding from thorium to uranium may be considered to consist of Mn positive ions that with a total of Ne electron for atoms. After plutonium, the metallic radius increases significantly again, which may reflect the increasingly lanthanide-like behavior of the later actinides, in which the preferred oxidation state is +3 with only 3 electrons per atom available for metallic bonding. Number 5, oxidation state. The actinide elements show a greater range of oxidation state than the lanthanides, particularly in the every part of the series. The different oxidation state of actinide elements are atomic number 89, actinide, oxidation state +3, atomic number 94, Pu, oxidation state +3, +4, +5, +6, +7, etc. The +2 oxidation state in case of actinides is very rare. Am2 positive has the electronic configuration 5f7. It is analog of Eu2 positive in the lanthanides but exists only in the solid state as a fluoride, AmF2. On the other hand, Cf2 positive, Es2 positive, Fm2 positive, Md2 positive, and NO2 positive exist as ion in solution. The properties of divalent actinides resemble more closely of barium2 positive in group 2. The most stable +2 oxidation state is exhibited by nobelium as NO2 positive and corresponding to stable 5F14 arrangement. The +3 oxidation state is the most common oxidation state among all the actinides. However, this is not always the most stable oxidation state in the actinides. The first 4 elements via TH, Pa, U and Np do not show +3 oxidation state as the most stable oxidation state. For example, U3 positive is readily oxidized in air as well as in solution. Interestingly, the most stable oxidation state of element up to uranium is the one involving all the valence electrons. Thus, the most stable oxidation state of TH, Pa and U are +4, +5 and +6 respectively, although neptunium shows the oxidation state +7 by involving all the valence electrons. Oxidation state +7 by involving all its valence electrons. It is not the most stable state. This is because Np in +7 oxidation state is highly oxidizing and the most stable state is +5. The plus 4 oxidation state is exhibited by all the elements from TH atomic number 90 to CF atomic number 96. However, Pa and Np display the most important plus 4 oxidation state. The M4 positive ions are known in the acid solution and are precipitated by F negative, PO4 3 negative and IO3 negative ions. The elements all form dioxides MO2 and fluorides MF4. The plus 5 oxidation state is exhibited by all the elements from Pa atomic number 91 to Am atomic number 95. However, plus 5 oxidation state is most stable for Pa and Np. It is important to note that MF5 positive M5 positive ions do not occur in solution as such. In fact, these states occur in as their oxocations such as MO2 positive ions. A few solid compounds are known whereas in solution their ions disproportionate rapidly. The plus 6 UO2 positive plus 4H positive product U4 positive plus UO2 2 positive plus 2H2. The plus 6 oxidation state is exhibited by lower actinides, example U, Np, Pu and Am, in the form of their fluorides. The plus 6 oxidation state is more commonly found as the dioxo ions, that is MO22 positive. The ions MO22 positive is linear and exists both in the solid as well as in the solution. One of the most commonly encountered compounds of uranium in plus 6 oxidation state is uranyl or anyl nitride dihydrate UO2 NO3 twice brought to H2. It consists of linear UO2 positive ion surrounding by two NO3 negative ion and water molecule as shown. The NO3 negative group are bidentate and therefore two oxygen from each NO3 are bonded to uranium. Oxygen atom from the two water molecule also bond to uranium. Thus, the coordination number around uranium is 8. The UO22 positive unit in the compound UO twice, NO3 twice, NO3 twice, H2O twice is perpendicular to a hexagon of 6 oxygen atom, 4 from bidentate NO3 negative group and 2 from water molecules. The lower oxidation state are ionic while the higher oxidation state are increasingly covalent. The plus 7 oxidation state is known only in the oxocation of Np and Pu when alkaline solution are oxidized by O3. The important oxoanions known in the case of Np and Pu are NpO4OH twice 3 negative and PuO6 3 negative. Number 6. Color of the ions. Actinides ion are mostly colored. The color of the particular actinide ion depend upon the number of electrons present in 5f orbital. The color of the actinide ion arises mainly due to FF transition. The color of the characteristic cation formed by the actinide ion via M3 positive, M4 positive, MO2 positive and MO2 positive in aqueous solution. In addition of the FF transition in actinides, the color can also arise due to FD transition as well as charge transfer transitions. The color of the actinide ion solution because of FF transition occur in the visible and ultraviolet region. We have already encountered this FF type of transition in case of lanthanides as well as since 5f electron in case of actinide are projected out more in space than the 4f electron in lanthanides. These 5f electrons are strongly influenced by the ligand field of ligands. This makes the absorption spectra of the actinides more complex compared to the straightforward spectra of lanthanides. A complex spectra is always different to characterized easily. It has been experimentally found that the absorption due to FF transition in case of actinides are nearly 10 times stronger and 2 times broader than the FF transition of lactinide series ions. The energy difference between 5f and 6d orbitals in case of actinide being smaller than 4f and 5d orbital. In case of lanthanides, the actinide ion inversely absorb light of lower frequency or higher wavelength. As a result, the allowed and very strong FD transition lie in the ultraviolet region and therefore do not influence the color of the actinide ions. It has been observed that the actinide ion in higher oxidation state display predominantly charged transfer spectra. This spectra is exhibited only by high oxidation state ions which can easily oxidize the ligands. It is important to note that lanthanides do not exhibit charge transfer spectra because lanthanides do not display oxidation state higher than 4. 7. Magnetic properties. The actinides show similar magnetic properties to lanthanides in terms of magnetic moment with the number of unpaired electrons. This is shown clearly where the magnetic moment in Bm are plotted against the number of unpaired electrons. It is important to note that the high valence state has been chosen for 5f1, 5f2, 5f3 and 5f4 ions which show the close similarities. Magnetic moment values for the isoelectronic actinide ion are lower than the lanthanide ion. Example Np6 and Ce3, Np5 and Pr3, Np4 and Nd3. This is due to the fact that 5f electron in actinide are projected more in space of the crystal field. As a result, the partial quenching of orbital occur by the crystal field effect. Number 8. Relativity. Number 8. Reactivity. The actinides are highly reactive metal. These react with dihydrogen and form non-stoichiometry hydrides with the formula MH2 or MS3. They react with hot water and tarnish in air, forming an oxide coating. The actinide react readily with HCl, but reaction with other acid is slower than expected. The metals are basic and do not react with sodium hydroxide. The actinides react directly with the halogen to form a variety of halides. The redox potential are known. The M3 positive to M couples are about minus 1.9 volt. Thorium and uranium chemistry has been exploited in detail. Some of the general methods for preparing compound of actinide are given below. Occurrence and isolation of actinides. All the elements beyond actinium in the periodic table are radioactive. As a result, the nuclei of all the actinides are unstable and undergo radioactive decay. Among the actinides, uranium is the heaviest natural occurring element with an abundance of 2.4 ppm in the earth crust and is more abundant than Ag and Hg. Among the actinides, Th and U occur on earth because the isotope of U92-235, U92-238, Th90-232 and Pu atomic mass 244 have half-lives sufficiently long in view of the fact that the earth was formed several million years ago. Uranium. Since uranium is the most important of the all actinides, its chemistry will be discussed in more detail. The primary natural source of uranium is pitch blende or uraninite, which has the empirical formula U3O8. It is the mixed oxide containing uranium both in 4 and 6 oxidation state in UO2 2UO3. The other important ore are carnotite, autunite, calcium carnotite. Extraction of uranium. As already mentioned, the main source of uranium is pitch blende. The detail of extraction of uranium involves the following steps. Number 1. Construction. The ore is crushed to a fine powder and is subjected to conventional gravity separation to remove the lighter impurities. Number 2. Roasting. The concentration ore is roasted on the hearth of a reverberatory furnace in the presence of air to remove the volatile impurities such as sulfur, arsenic and antimony. S plus O2 S2O. S plus O2 SO2. Number 3. Acid treatment. The roasted ore is treated with dilute H2SO4 in the presence of oxidizing agents such as MnO2 or NaClO3. This treatment converts uranium to a soluble uranyl sulfate UO2SO4. The roasted ore can also be converted to a solution of UO2NO3 twice by dissolving the ore in nitric acid. U3O8 plus 3H2SO4 plus O product 3UO2SO4 plus 3H2O. Number 4. Treatment with ammonium carbonate. Addition of ammonium carbonate to the above solution of uranyl sulfide precipitate it as ammonium uranyl carbonate. UO2SO4 plus 3 4H4 twice CO3 product NH4 UO2 CO3 whole thrice plus NH4 whole twice SO4, which upon ignition gives U3O8 as NH4 whole 4 UO2 CO3 whole thrice product U3O8 plus 9 CO2 plus 12 NH3 plus 6 H2O plus O2. Alternatively, ammonia is added to the solution of uranyl sulfate obtained in step 3 acid treatment. This gives rise to bright yellow precipitate of ammonium diuranate NH4 twice U2O7. This precipitate is often called the yellow cake. This cake on heating gives rise to mixed oxide uranium 4 and uranium 6 oxide, that is U3O8 equivalent to UO2 to UO3. 9 NH4 twice U2O7 solid heat देके product 6 U3O8 plus 14 UH NH3 plus 15 H2O plus N2. Number 5, conversion into uranium dioxide. The mixed uranium oxide U3O8 is reduced to UO2 by heating either with charcoal or with hydrogen. U3O8 reactant U3O8 plus 2 H2 product 3 UO2 plus 2 H2O. Production of uranium. Elemental uranium can be produced from uranium dioxide by using either of the two methods. Number 1, UO2 is heated with vapor of HF2 from form uranium 4 fluoride, which in turn react with magnesium to yield uranium metal UO2 plus 4 HF product UF4 plus 2H2, or by converting UO2 to a volatile uranium tetrachloride by heating it with elemental chlorine in the presence of charcoal. This is followed by reduction with elemental sodium UO2 plus Cl2 UO2 Cl2. All the step detail above can summarized in the following flow sheet diagram for the extraction of uranium. Chemistry of separation of neptunium Np, plutonium Pu and americium Am from uranium. The three elements neptunium, plutonium and americium that follows uranium in the actinide series are produced mainly from uranium in the nuclear reactors. If you recall, uranium is the oldest known element among the actinides. Naturally occurring uranium contains two main isotopes, that is U atomic number 92, atomic mass 238 and U atomic number 92, atomic mass 235, which occur in the ratio 99.3% or 0.7% respectively. This is another isotope of uranium, atomic number 92, mass number 233, which occur in traces only. Neptunium and plutonium, named after the planets Neptune and Pluto, were prepared for the first time in 1940 by a team of celebrated scientists by bombarding uranium with neutrons in the cyclotron in Berkeley, USA. Both the elements are now obtained from spent uranium fuel elements of nuclear reactor, where they are formed by the capture of neutrons produced in the fission of uranium 92 to 9235 fuel as. Isotope of plutonium Pu can also be prepared by N2N reaction, in which a fast neutron is added with the subsequent loss of two neutrons without allowing time for the intermediate product to decay. U92 to 238 N2N U92, atomic number 92, mass number 237. Beta uranium, atomic number Np, atomic number 93, mass number 237. Americium can be obtained from the isotope of plutonium by the success of N-gamma reaction in the nuclear reactor. Pu 94 to 239 and gamma Pu 94, mass number 240 and gamma Pu, atomic number 94, mass number 241. Beta Am, atomic number 95, mass number 241. The yield of the heavier element after americium is controlled by two factors. Number 1, the half-lives of the various isotopes. Number 2, by their ability to absorb neutron. It is important to note that the stepwise addition of the slow neutron is very difficult. A quick method is to bombard the nucleus with a large number of fast neutron without allowing time for the intermediate product to decay. For example, U92 to 238 adds a fast neutron and then loses 2 neutrons to form an isotope of neptunium according to the reaction. U atomic number 92, mass number 238, N2N U atomic number 92, mass number 237, beta Pu 93, atomic number, mass number 237. The separation of these elements and Pu and Am from uranium is extremely difficult and hazardous. It is because these elements, including the starting material, are not only highly radioactive but also give high radioactive fission product. Plutonium especially is extremely toxic. A dose of as small as 10 to the power minus 6 gram may be fatal, while smaller doses are carcinogenic. The separation of Np, Pu and Am from U are based on the following chemistry. Number 1, stability of oxidation state. A steady decrease in the stability of high oxidation state with the increase in atomic number have been observed with the increase in atomic number. The order of stability of the major ion involved are Am3 positive greater than Pu3 positive greater than Np3 positive U positive. Order in the case of oxo ions, UO2 positive greater than NpO2 positive, PuO2 positive, AmO2 positive. Separation of these elements from uranium from which they are obtained in the nuclear reactor from fission product and from one another can thus be achieved by adjusting the solution containing them to a suitable redox potential, and these then using solvent extraction or precipitation. For example, Pu can be oxidized to PuO2 positive while Am remain as Am3 positive, as thus plutonium Pu can be removed by solvent extraction, whereas americium can be precipitating as AmF3. Number 2, extraction into solvent, organic solvent. MO2 positive ions solution can be extracted into organic solvents. The M4 positive ion are extracted into tributyl phosphate in kerosene from 6-MHNO3 solution, whereas M3 positive ion are extracted from 10 to 16 molar HNO3. Number 3, precipitation reaction. Actinides in the +3 and +4 oxidation state can be precipitated as their fluorides or phosphate from acid solution. The higher oxidation state beyond +4 give either no precipitate or can be prevented from precipitation by complex formation with sulfate ions. Number 4, ion exchange method. Ion exchange method are commonly used in the separation for small amount of material, as in the separation of americium, Am, spent uranium fuel rods removed from the nuclear reactors can be used to extract Np and Pu in kilogram quantities, whereas Am in 100 gram quantities. This reprocessing of nuclear fuel rods is an important technology, as this helps to extract new element that may be used as nuclear fuel. Spent fuel rods are dipped in ponds of water for several days to allow them to cool. During this dipping period, intensely radioactive isotope with short half-life such as I-53151 lose most of their activity. The fuel rods are dissolved in 7 molar HNO3 and extracted with 30 tributyl phosphate TBT in kerosene, and extraction coefficient of actinide in 7 and HNO3 solution containing 30% tributyl phosphate in kerosene are UO2 positive, NP greater and PO2 positive, PuO2 positive. The M3 positive ion have very low extraction coefficient in 7 and HNO3. As a result, nitrates of UO2 positive and Pu4 positive are preferably extracted in the tributyl phosphate, leaving the other actinides, namely Np and Am, along with the other fission product FPS in aqueous solution. It is also important to note that 7 normal HNO3 cannot oxidize Pu4 positive to higher oxidation state through Pu5 and Pu6 reduction of UO2 positive to Pu4 positive or Pu4 nitrate solution with SO2 NH2OH or Fe NH2SO3 twice give aqueous solution of Pu plus 3 without affecting the reduction of UO2 positive. The Pu4 positive is reduced to Pu3 positive, which enter the aqueous phase, while UO2 positive remain unchanged in organic layer. UO2 positive Species present in kerosene oil on treatment with 0.2 normal HNO3 give UO2 NO3 twice in the aqueous solution, which on evaporating leaves a solid mass of composition UO2 NO3 twice. 6H2 on heating this hydrated solid compound to 400 degrees Celsius gives UO3, which upon further reduction yield UO2. On the other hand, aqueous solution of reduced Pu3 solution on treatment with nitrous acid gets oxidized to Pu4. This solution reacts with oxalic acid to give crystalline precipitate of the composition PuC2O4 twice 6H2O. Heating the hydrate compound to 300 degrees Celsius give PuO2. The whole sequence of steps outlined in the process are described. The separation of other actinide, namely NP and AM, can be achieved by the use of appropriate oxidation reduction cycle coupled with solvent extraction. For example, Pu3 positive in aqueous nitric acid can be oxidized to PuO2 positive by the N-oxidizing coupled with EU greater than 1.02 volt, followed by the extraction into hexane, whereas Am3 positive is unchanged and remain in aqueous solution. Transuranic elements. Element which an atomic number greater than 92 are called transuranic element. Before the Second World War, the element thorium, protactinium and uranium were located below the hafnium, tantalum and tungsten in the periodic table. The synthetic of neptunium, a new element with atomic number 93 by M.C. Millan and Abelson in 1940 was demonstrated by bombarding uranium with neutron U, atomic number 92, mass number 238 plus N0 to 1 U 92 to 239 beta NP 93 to 239. This newly discovered element should be positioned immediately to the right of the tungsten below rhenium. However, the properties of neptunium resembled more with uranium rather than rhenium. It was discovered of neptunium, followed by the subsequent synthetic of new elements that were responsible for the new series of elements called the actinide series. All the transuranic elements were radioactive in nature and have short half-life period. Neptunium, atomic number 93, plutonium and americium were unknown prior to their synthetic preparation through nuclear reaction. However, these elements were later found to be present in trace quantities in uranium ores. Synthetic route to transuranic element. Synthetic routes to transuranic elements. These are two synthetic routes which are commonly used for the synthesis of transuranic elements. A neutron may be captured by the nucleus with the emission of gamma rays reaction. The neutron increases the mass number of the nucleus by 1 unit and some energy is released as gamma radiation. Further, neutrons may be added in a similar way. Addition of neutrons increases the neutron to proton, the N by P ratio. This makes the nucleus unstable because it contains too many neutrons. As a result, the nuclei decay by converting a neutron into a proton and a beta particle, that is an electron. This reduces the N by P ratio and also increases the atomic number by 1. Thus, a new element is formed. Uranium, atomic number 92, mass number 238 plus neutron 0 to 1. Product uranium 92 to 239, beta NP 93 to 239. The other method involves the capture of small ions by the heavy nucleus. This is possible only if the bombarding particle have sufficient energy to overcome the Coulombic repulsion between the ion and the heavy nucleus. The smaller ions are accelerated in a linear accelerator or cyclotron to possess sufficient kinetic energy. The simplest ion used in the alpha particle, that is helium nucleus. This increases in the atomic mass unit by several units and the atomic number by 2 units. For example, Pu, atomic number 94, mass number 244 plus helium He, atomic number 2, mass number 4. Product Cm atomic number 96, mass number 248. Synthesis of transuranic elements. All the transuranic elements have been prepared by nuclear reaction, which involve bombardment with either the neutron, alpha particle, or other small nuclei. Preparation of neptunium, atomic number 93. It was prepared by MC Millian and Abelson in 1940 at Berkeley, USA by bombarding uranium-92 to 238 with slow neutron when uranium-92 to mass number 239 was obtained. Uranium, atomic number 92, mass number 239, being unstable, emits beta particle and result in the formation of neptunium, Np, after the name of the planet Neptune. Preparation of plutonium, atomic number 94. It was discovered by C. Borg and his co-workers during the beta decay of neptunium-239. Np, atomic number 93, mass number 239. 2Pu, atomic number 94, mass number 239, plus electron. Plutonium was named after the name of the planet Pluto. Preparation of americium, atomic number 95. Americium was synthesized by bombarding uranium-92 to mass number 238 with alpha particles as uranium, atomic number 92, mass number 238, plus helium-224, मिलके product Pu-94 to 241 plus neutron. Pu-94 to mass number 241 product Am, atomic number 95, mass number 241, plus electron. Preparation of curium, atomic number 96. Curium was synthesized by bombarding Pu-94 to 239 with alpha particles as reactant. Pu-94, atomic number, mass number 239, plus helium-224, product Cm, atomic number 96, mass number 242, plus neutron. Preparation of berkelium, atomic number 97. Berkelium was synthesized by C. Borg and his co-workers by bombarding americium-241 with high-speed alpha particle. Preparation of californium, atomic number 98. Californium was synthesized by bombarding curium-242 with alpha particle. Cm 96 to 242 plus helium gives product Cf98 to 244 plus gamma rays or neutron. Preparation of einsteinium, atomic number 99. Einsteinium was synthesized by bombarding uranium-238 nucleus with accelerated nitrogen nuclide. Two isotopes of californium have been identified: uranium-92 to 238 plus and 7 to 14 nitrogen as product Es99, mass number 247, plus neutron. It can also be prepared by bombarding isotopes of californium-250 with neutrons. Californium-253 obtained during bombardment process result in beta decay formation. Einsteinium. Preparation of fermium, atomic number 100. Fermium was synthesized by bombarding Einsteinium-253 with neutron as Einstein 99 to 254 plus neutron gives Einstein 99 254 plus gamma ray. Einstein, atomic number 94, mass number 254, gives Fm, atomic number 100, mass number 254, plus electron. Preparation of mendelevium, atomic number 101. Mendelevium was synthesized by bombarding Einsteinium-253 with alpha particle as Es99 to 253 plus helium gives Md101 to mass number 256 plus neutron. Preparation of nobelium, atomic number 102. Nobelium was synthesized by bombarding curium-246 with accelerated stripped carbon C6 plus. Cm96 to 246 plus carbon gives product nobelium NO, atomic number 102 to mass number 254 plus neutron. Preparation of lawrencium, atomic number 103. Lawrencium was synthesized by bombarding californium-250 with accelerated boron nuclei. Cf98 to 250 plus boron 5 to 11 gives product lawrencium, atomic number 103, mass number 257 plus neutron. A summary of synthesis of transuranic element along with the half-life of the element. The later of heavier actinide element. The element from curium onwards, namely curium, berkelium, californium, einsteinium, ferium, mendelium, fermium, mendelium, nobelium, and lawrencium are named as later actinides. Very little is known about the chemistry of these later actinides because of their limited availability and extreme instability. The availability of some of the most accessible isotopes are given. It is clear from the table that curium is available only in macroscopic quantities, whereas the later actinides about atomic number 100 have been prepared only in minute quantities of the in minute order of few minutes. In words, later actinides are available in tracer amount. It is interesting to note that the later actinides show close resemblance to the lanthanides. However, the actinide can be easily separated from the lanthanide because the actinide readily form complexes. For example, the actinide react with concentrated HCl to form the corresponding chloro complexes in both group of ions are absorbed on the cation exchange column. The actinides can be eluted more conveniently with concentrated HCl. After eluting the actinides can be separated from each other by ion exchange using citrate solution to elute them. It is interesting to note that the order in which the tri-positive actinide ion are eluted shows a close similarity to the order in which the tri-positive lanthanide ion are eluted. Display the elution diagram for the actinide and the lanthanide element. The first identification of element from americium to Mendeleev on a weighted scale was made through elution. All the actinides with atomic number 96 to 103 with the expectation of nobelium have as the +3 as the most stable oxidation state. The most stable oxidation state of nobelium is +2. This is because it is the most favorable F14 electronic configuration. Actinides with atomic number 98 to 102, that is californium, 98 to nobelium, atomic number 102, also display +2 oxidation state except for nobelium. +2 oxidation state is strongly reducing in nature. Higher oxidation state of curium, Cm+4, are found in the solid state in compounds such as CmF4 and Rb CmF5. CmF4 plus RbF5 product RbCmF5. Similarly, berkelium compounds are stable in the +4 oxidation state such as BkO2 and CS2 BkCl6. Lawrencium atomic number 104 exists only in the +3 oxidation state and resists oxidation and reduction. This resistance to oxidation, that is +4, and reduction, that is +2, illustrate the stability of an F4 electronic configuration. The elements up to atomic number 100 undergo radioactive decay mainly by emitting alpha particle or beta particle. The later element becomes increasingly unstable as the atomic number increases. Nobelium is extremely unstable and has a half-life of only 3 seconds. Element beyond atomic number 103. The actinide series is complete at lawrencium atomic number 103 Lw. We have already learned that the half-life of later actinide beyond atomic number 100 decreases considerably. For example, the half-life of nobelium is only 3 seconds. It has been calculated that the half-life of the element will decrease further as new elements are discovered. The half-life of element with an atomic number 108 is expected to be very short, about 10⁻⁴ to 10⁻⁶ seconds due to spontaneous decay. As a result, it is extremely difficult to synthesize and study the chemistry of element beyond 108. However, these difficulties have not dampened the spirit of the scientist, and they have been successful in discovering element up to atomic number 112. Out of 112 known elements, element up to atomic number 109 have so far been named. A major controversy came to light over naming these elements. The choice of the name of element belongs to the discoverers. In the case of postactinoids, 3 nuclear facilities are in competition for the synthesis of each of the now newly discovered element. The facilities are at Berkeley, California, USA, Dubna, Russia, and Germany. It is extremely difficult to identify which nuclear facility had the true claim. For example, the discovery of element 104 was claimed by both Berkeley and Dubna, Russia groups. The Americans named the element Rutherfordium, while the Russians named it Kurchatovium. While these conflicting claims were being settled, the International Union of Pure and applied chemistry, IPAC devised a hybrid Latin Greek numerical system of providing provisional names and symbols to all the newly discovered elements. Names are derived directly from the atomic number using roots for the 3 digits in the atomic number of the element or adding the ending em. In some cases, the names are shortened by removing the repetitive letter. Example, bi plus em can be written as biem or triem, can be written in short form as triem. Let us name an element with atomic number 106 according to hybrid Latin Greek nomenclature. The name of the element is derived by combining together the roots in the order of digit which make up the atomic number followed by adding em in the end. 106 un plus nil plus hex plus em, unyl hexium. The symbol for the element unyl hexium with atomic number 106 is UNH. The IPAC name for the atomic element with atomic number more than 100 are given. More than 100 are given. Comparison of actinides and lanthanide. Both lanthanide and actinide constitute element of F block as these involve the gradual filling of F orbital. These elements occupy a distinct safe space at the bottom of the periodic table. They show close resemblance in some of their properties but also differ in many properties. Let us review some of important point of similarities and differences among the lanthanoids and actinoids. Point of similarities. Both the lanthanoid and actinoid involve the filling of F orbital. Number 2. Both the lanthanoid and actinoid display predominantly the +3 oxidation state in most of their compound. Number 3. Due to poor shielding of 4f and 5f electron, both lanthanide and actinide show gradual contraction in the size of their atoms with increase in atomic number known as lanthanide and actinide contraction respectively. Number 4. Element of lanthanide and actinide with the same number of unpaired electrons display similar absorption spectra due to FF transition. Number 5. Lanthanides and actinides are highly electropositive and are very reactive. Number 6. Nitrate, sulfate and perchlorate of trivalent lanthanides and actinide are soluble in water. Number 7. Hydroxide, fluoride and carbonate of trivalent lanthanide and actinide are insoluble in water. Both lanthanides and actinides can be separated by ion exchange method. Point of separation. Point of difference. Important point of difference between lanthanide and actinide are presented. Difference between lanthanide and actinide. Property. Number 1. Metal orbital. Lanthanide, it involves filling of 4f orbital. Actinide, it involves filling of 5f orbital. Number 2. Energy gap between f and d orbital. Lanthanide, the gap between 4f and 5f orbital in lanthanide is very large. As a result, their chemistry is fairly similar. Actinides, the energy gap between 5f 60 and in actinides is small. As a result, their chemistry is very difficult. Number 3. Binding energy. Lanthanide, binding energy of 4f orbital are higher in lanthanide. Actinides, binding energy of 5f orbital are lower in actinides. Number 4. Oxidation state. The most common oxidation state is +3 in addition to some lanthanide showing +2 and +4 actinide. The common oxidation state in +3 in addition to some actinide showing +2, +4, +5, +6. Number 5. Shielding effect. 4f electron exert greater shielding effect. Actinide, 5f electron exert poor shielding effect. Number 6. Ability to form oxocations. Actinide, lanthanide do not form oxocation. Actinide form oxocation in higher oxidation state. Example, UO22 positive. Number 7. Color of the ion. Most of lanthanide ion are colorless. Actinide, most of the actinide ion are colored. Example, U3 positive red, U4 positive green, UO22 positive yellow. Number 8. Complexing ability. The tendency to form complexes is small. The tendency to form complexes is large in actinides. They do form complexes with pi bonding ligands. Number 9. Radioactivity. All lanthanide except promethium are not radioactive. All the actinoids are radioactive. Number 10. Coordinate number. Lanthanide display coordination number 6, 7, 8 and 9. Actinide display higher coordination number 8, 9 or 10. Number 11. Basic character. Compound of lanthanide are less basic in character. Compound of actinide are more basic in characters. Thank you.